Was the universe really made up only of structures that swallowed everything? While one point of space-time pulled everything in, was the universe spewing matter and energy back out at another point? Black holes had become the most terrifying and best-known cosmic structures of modern science. Yet directly opposite them stood a possibility much less discussed, one filled with far more question marks: white holes. These hypothetical structures, which let nothing in but have everything flowing out, represented one of the most radical ideas challenging the one-way operation of the universe. White holes have never been directly observed to date. Nevertheless, the equations of general relativity, which form the basis of modern physics, made the existence of such structures mathematically possible. But did everything mathematically possible also occur physically? Or were white holes just theoretical ghosts trapped within the equations? These questions placed white holes at the center of a deep inquiry into the nature of the universe, elevating them from mere cosmological concepts. The path to understanding white holes inevitably led to black holes. When massive stars exhausted their fuel at the end of their lives, they collapsed under their own mass, warping space-time so extremely that they formed black holes. In these regions, the boundary called the event horizon was crossed, and beyond this limit, nothing, not even light, could return. Black holes were one way, entry was possible, but exit was impossible. However, when Einstein's equations of general relativity were examined, an unexpected symmetry emerged. The equations offered solutions not only for the forward direction of time, but also for a reverse direction. When the mathematical solution of a black hole was reversed in time, an entirely different structure appeared, a structure that didn't swallow everything, but expelled everything outward. This reverse solution was named a white hole. At this point, an important question arose. Did every black hole have a white hole counterpart? Mathematical symmetry did not rule out such a possibility, but it became clear that this was not a necessary rule in the physical universe. Only in some theoretical models, under certain conditions, could a link be established between black holes and white holes. In other words, not every black hole inevitably resulted in a white hole. A white hole, in its simplest form, was defined as a region of space-time into which nothing could enter, but from which matter and energy flowed outward. Like black holes, white holes also had an event horizon. However, this horizon worked in the opposite direction. While the event horizon of a black hole locked everything inside, the event horizon of a white hole pushed everything out. This naturally posed the question, why could nothing enter a white hole? The answer lay in the geometry of space-time. The internal structure of a white hole was shaped so that causal connections were only allowed outward. The inside of the event horizon established only a one-way relationship with the outside universe. Physically, there was no path that progressed inward. Even light could not cross this boundary. White holes challenged not only the concept of space, but also the concepts of time and causality. Did time really flow backward in white holes? From the perspective of general relativity, the direction of time did not actually change, but white holes appeared as extreme points where time operated only in a consequence-generating manner. This created the impression that results existed without causes. Here, a more disturbing question emerged. Did white holes break causality? Theoretically, yes, because to an outside observer, the matter and energy emitted from a white hole seemed to have no apparent cause. This explained why white holes were considered physically problematic. The problems did not end here. The second law of thermodynamics stated that entropy in the universe increases over time. Black holes were compatible with this law. By swallowing everything, they increased disorder. White holes, on the other hand, required an orderly, low-entropy output, which made them extremely fragile physically. At this point, an inevitable question arose. Were white holes stable structures? According to existing theories, no. The slightest external interaction would disrupt a white hole structure and cause it to collapse instantly. Therefore, white holes were thought to be structures that vanished as soon as they were formed, with extremely short lifespans. White holes were often mentioned together with wormholes. Theoretically, a connection called an einstein-rosenbridge could be established between a black hole and a white hole. In this case, the black hole acted as an entry and the white hole as an exit. However, this idea brought new questions. Was it possible to pass through such a structure? According to current laws of physics, the answer was negative. Einstein-Rosen bridges were extremely unstable and collapsed instantly when matter tried to pass through them. Therefore, even though wormholes were mathematically possible, they were not practical cosmic tunnels that could be traversed. The most striking dimension of white hole discussions reached the beginning of the universe itself. The Big Bang began with everything being ejected from an extremely dense and hot point. This description bore remarkable similarities to the behavior of a white hole. So was the Big Bang really a giant white hole? This possibility has not been completely ruled out. In fact, some models suggest that our universe may have originated from the inside of a black hole in another universe. Yet here a critical question emerged. If the Big Bang was a white hole, was this process still ongoing? According to cosmological models, this process was limited only to the universe's earliest moments. The expansion we observe today no longer results from a white hole-like outflow, but from the general dynamics of the universe. To date, there have been no direct observations of white holes. Among the reasons for this are their extremely short lifespans, their lack of distinctive observational traces, and the fact that current telescopes cannot clearly distinguish such events. Still, this question remains alive. Could it be possible to detect white holes in the future? Theoretically, this possibility is not completely ruled out. More sensitive gamma-ray detectors and advances in quantum gravity theories could help identify signals unique to white holes, but for now, this remains a distant possibility. In recent years, quantum gravity approaches have added a new dimension to the concept of white holes. According to these models, instead of black holes disappearing entirely, they may transition to a white hole phase over extremely long timescales. This answered another question: do white holes form after black holes? According to some theories, yes. However, this transformation could take trillions of years and would be almost imperceptible to outside observers. This offers a possible reason why white holes have not been recognized until now. In conclusion, white holes remain one of the most radical concepts, suggesting that the universe might contain not only swallowing, but also outward exploding structures. Even though they have not been observed yet, these structures, which question the direction of time, causality, and the cosmic beginning, continue to push the boundaries of modern physics. One thing is certain: white holes represent one of the furthest intellectual frontiers reached by the human mind, striving to understand the universe. I've shared what is wondered about one of the most extraordinary structures in the universe, white holes. If you want to see more content like this, don't forget to like and subscribe. I look forward to your questions and comments.